The next two colligative properties that we're going to learn about go hand in hand with one another, and that is freezing point depression and boiling point elevation. What that means is when we compare a pure solvent to that of a solution, the solution is always going to boil at a higher temperature than that of the pure solvent. And since it's freezing point depression, the solution will always freeze at a lower temperature than that of the pure solvent. This picture right here shows us a phase diagram. A phase diagram tells us what unique pressure and temperature combinations will give us different phases of a substance. So on the left here, this represents the pressure and temperatures where something will be a solid. This represents the pressure and temperatures where it'll be a gas. And in the middle, it represents the different pressure and temperatures where something will exist as a liquid. This unique point right here, where all three lines come together, is called the triple point. The triple point is a unique pressure and temperature which represents where all three phases can coexist in equilibrium. The green lines represent the pressure temperature combinations for that of a pure solvent. So anywhere along that line would be an equilibrium between the liquid phase and the gaseous phase. Whereas anywhere along this green line would represent temperature and pressure combinations where the substance would be in equilibrium between the solid and the liquid phase. 1 atmosphere of pressure is considered normal external atmospheric pressure. Where that liquid-gas phase boundary line crosses the 1 atmosphere of pressure location is where we would refer to the normal boiling point of a solution. Normal boiling point meaning it boils at 1 atmosphere of pressure. Really anywhere along that liquid-gas equilibrium line at different pressures could represent other boiling points for that pure solvent. And where the liquid-solid phase boundary line crosses 1 atmosphere, this point would represent our freezing point of our pure solvent at 1 atmosphere of pressure. Now, we previously learned that when we make a solution and we dissolve a solute into a pure solvent, that it lowers the vapor pressure of the solution. That was Raoult's law. Since the vapor pressure gets lower, the whole boundary line between the liquid phase and the gas phase gets dropped. It gets dropped to lower position on our triple phase diagram graph. This lowering of the vapor pressure also causes the triple point for that of our solution to be at a lower pressure and temperature as well, which also shifts the phase boundary line between the solid and the liquid phase to lower temperatures as well. One thing that's unaffected is the phase boundary line between solid and gas. The solid and gas phase are not impacted by our solution that we're creating, so those pressure and temperatures would remain the same. What we can see is that there is a difference between the boiling point of our pure solvent and of our solution that we created. The difference between those two is represented by delta T sub B. That shows us the change in the boiling point, and everywhere along the way the boiling point is going to be higher for the solution than that of the pure solvent. There's also a difference in freezing point. This would be our freezing point of our solution, and everywhere along the line, it's lower for that of our solution than of our pure solvent. This is represented by delta T sub F, or the change in the freezing point. Therefore, by having solute dissolved in a solvent, the vapor pressure falls because the solute particles block the escape of the solvent particles, causing the freezing point to be lower and the boiling point to be higher of the solution. We previously learned that the boiling point of a liquid is when the vapor pressure is equal to the external atmospheric pressure. So boiling points can change depending upon your elevation. A liquid will boil at a different temperature if you're up in the mountains in Colorado than if you're down in a valley. When we're talking about boiling point, we're usually referring to the normal boiling point, which is the boiling point at 1 atmosphere pressure. So when someone says what the boiling point is, they're usually referring to that normal boiling point. We learned that when we add a solute to a solvent, we lower that vapor pressure, and we saw on the previous slide that that shifted that liquid-gas phase boundary line down lower. That is what caused our boiling point to be higher, or we saw the boiling point was elevated for our solution. This is what we do when we add salt to water before we make pasta. We're trying to increase the temperature that the water will boil at, and therefore it will boil at a higher temperature and the pasta will be able to cook faster. Similarly, with freezing point depression, we saw that the vapor pressure lowering of a solution caused that solid-liquid phase boundary line to also be shifted lower as well. This is what caused freezing point depression, or our solution to freeze at a lower temperature than that of the pure solvent. This is the principle that's employed when they salt roads in order to help keep them from freezing over. Different solutes added or different salts on the road will cause a lower freezing point than others. So there are some salts that are very good and some salts that are not so good. Boiling point elevation and freezing point depression are both colligative properties, meaning that how high the temperature can be raised for the boiling point and how low it can be depressed for the freezing point depends only upon the number of particles in solution, and not the identity of those particles. So it doesn't matter what they are, just matters how much of them are present. So let's look at the different formulas for this. The change in the boiling point for a solution from a non-volatile non-ionic solute, first we'll start by looking at non-volatile non-ionic solutes overall, is delta TB equals mKb. Delta TB equals the change in the boiling point temperature, where that Greek letter delta usually represents change. M is the molality of the solute, so we're using lower m. And K sub B is the boiling point elevation constant. That's a constant that will depend directly upon the solvent that is used to make the solution. There's a table of these in your book, and we'll use some common ones throughout this class. The change in the freezing point, or delta TF, is equal to MKF. Delta TF will be the change, so we're going to have to figure out what the real freezing point is in order to see how it changes. Little m is still molality, so moles of solute per kilogram of solvent. And K sub F represents the freezing point depression constant. Just like K sub B, that will directly depend upon the solvent that's being used to make up the solution. Here are some common boiling point elevation and freezing point depression constants to have on hand while you're doing your homework. Commonly, we'll have aqueous solutions, so that means the solvent is water. The K sub B for water is 0.51 degrees C per molal, and the K sub F is 1.86 degrees C per molal. Ethyl alcohol has a K sub B of 1.22 and a Kf of 1.99, and benzene has a Kb of 2.64 and a Kf of 5.07. So make sure when you're looking at the problem that you're reading what the solvent is, and then you're using the correct depression constants or elevation constants for that solvent. Calculate the boiling point of a solution that contains 1.5 grams of glycerol in 30 grams of water. Notice glycerol's chemical formula is C3H8O3. It's all nonmetals together. So this represents a non-ionic solute, which is important because so far we've been only using non-ionic, non-volatile solutes, meaning they won't escape from the solution if they're non-volatile. In this case, we're calculating a boiling point of a solution. So we're going to use delta T sub B equals mKb. First, we have to calculate the molality, and then since our solvent is water, the K sub B, or the boiling point elevation constant for water, is 0.51 degrees C per molal. Let's convert our 1.5 grams of glycerol into moles. We know that the molar mass is 92 grams per mole. So that gives us 1.63 times 10 to the negative 2 moles of the glycerol. Calculating our molality, which is equal to the moles of solute per kilogram of solvent. We're going to take our moles of glycerol and plug them into the numerator. 1.63 times 10 to the negative 2 moles, divided by our solvent, which is water, in kilograms. So we have 30 grams of water, which is equivalent to 0.030 kilograms of water. Our molality comes out to 0.543 molal. Now we can plug that into our boiling point elevation equation. Delta T sub B equals our molality, or 0.543 molal, times our boiling point elevation constant, 0.51 degrees C per molal. We can see that our units of molality will cancel, and our delta TB will be in units of degrees Celsius. Delta TB comes out to being 0.277 degrees Celsius, but this is not the boiling point of our overall solution. The boiling point of our solution will equal our boiling point of our solvent, which in this case is water, plus our delta T sub B, or our change in our boiling point. So we know that water normally boils at a temperature of 100 degrees Celsius, plus we have to add our delta TB we just calculated, 0.277 degrees Celsius. So overall, our new solution will boil at 100.277 degrees C. 15 grams of an unknown compound dissolved in 100 grams of water lowered the freezing point to negative 2.6 degrees Celsius. Determine the molecular weight of the compound. We're talking about freezing points, so that means we're going to be using our new formula, delta TF equals mKF. We're going to assume that our unknown compound is still a non-ionic, non-volatile solute, and it's being dissolved in water, so water is our solvent. So we have an aqueous solution. The K sub F, freezing point depression constant for water, is 1.86 degrees C per molal. Since we're figuring out an unknown molecular weight this time, that means we're calculating some grams of solute per mole of solute. They told us in the problem that the number of grams of our unknown solute was 15 grams. So we don't know the number of moles. We're going to have to use our delta TF formula in order to figure out moles. And the only term in that formula that has anything to do with moles is the molality of the solution. So we can rearrange to solve for the molality. Another note is that our freezing point is actually negative 2.6, but that's not the delta TF. The freezing point of the solution would be equal to the freezing point of the pure solvent minus the change in the freezing point, delta TF, because we know that the freezing point is going to be lower for a solution compared to a solvent. So if we're dealing with water, water has a freezing point normally of 0 minus the delta TF would be equal to negative 2.6 degrees Celsius, because we know the solution froze at negative 2.6 degrees Celsius. So if we were to rearrange and solve for delta TF, that would be equal to positive 2.6 degrees Celsius. So when we plug that into our formula, we want to make sure that we use a positive value, because molalities should never be negative, and the freezing point depression constant should also never be negative. If we rearrange and solve for the molality, molality will be equal to delta TF divided by K sub F. We know delta TF is positive 2.6 degrees C, and KF is a constant, 1.86 degrees C per molal. Our degrees C's will cancel, and our 1 over molality will flip to just become units of molality. So the molality of this solution is equal to 1.398 moles per kilogram. From that, we have to be able to figure out just the number of moles of solute, not the moles of kilogram. So that's where knowing the amount of solvent that's used is important, because molality is moles of solute per kilogram of solvent. So our molality is equal to some moles of solute in the numerator, we'll call it X, divided by, we had 100 grams of water, which converting that to kilograms is 0.100 kilograms of the water. We can solve for the moles of solute by multiplying the molality, 1.398 moles per kilogram, times our denominator, 0.100 kilograms. We can see that the kilograms will cancel and we're left with units of moles now, which is what we were after. So the moles will end up being 0.1398. And that's what we're going to end up plugging into our denominator for our molecular weight calculation. That's what we were trying to figure out, was the number of moles, so we could calculate the molecular weight of our unknown. So molecular weight will be equal to 15 grams of solute per 0.1398 moles of solute, which comes out to being about 107 grams per mole. The last of the colligative properties that we're going to learn about is called osmotic pressure. But before we can dive right into learning about osmotic pressure, we first have to learn about something called osmosis. Osmosis refers to the movement of solvent particles through something called a semi-permeable membrane. The solvent particles will move from a chamber of less concentration to a chamber of more concentration. Therefore, the concentrations that are split between the two sides of the membrane will become equalized. Living cells are surrounded by semi-permeable membranes. They allow the passage of small solvent particles, but they block larger solute particles. The picture on the left shows us what happens during osmosis. On the left-hand side, we have a chamber that contains pure solvent. So that would be the one they're referring to as low sugar concentration, where the green circles are representing sugar particles. It's separated by the right-hand chamber by a selectively permeable membrane, or a semi-permeable membrane, sometimes called an osmotic membrane. This is a membrane that will only allow the water particles or the solvent particles to pass through from the left hand to the right-hand side. On the right-hand side, we have a high sugar concentration. There's more solute particles of sugar than there are on the left. So the water will leave the left-hand side and move to the right-hand side through that semi-permeable membrane to allow more water to go to the right in order to dilute the sugar concentration and try to make the solutions equalized in concentration. Therefore, we see the level of the water lowering on the left-hand side and rising on the right. Another way to think about this is if initially we have two solutions separated by an osmotic membrane, which is semi-permeable, and we have two different concentrations. Initially, we have one concentration that is 0.1 molar, and we have one that is 0.2 molar, where the orange spheres can represent our dissolved solute particles, where we have 3 particles on the left-hand side and 6 particles on the right to represent that it's more concentrated. This means that through osmosis, water, which is our solvent filling the container, will flow from the left chamber, which has a lower concentration, to the right chamber, which has a higher concentration, trying to dilute the higher concentration solution, and it'll raise the concentration of the 0.1 molar because solvent particles are leaving. So after some time, what this chamber would look like then, it'd still be split by a semi-permeable membrane, but the level of liquid in the left-hand side compartment would go down, and the level of liquid in the right-hand side compartment would go up. We would still have 3 solute particles, and we would still have 6 solute particles over here, but now the concentrations have changed. Now we can imagine that the concentration on the left might be 0.15 molar because we have those same 3 particles, but they're in a lower amount of solvent. And the chamber on the right is now 0.15 molar because those same 6 particles are in a greater amount of solvent. Therefore, M1 has become the same concentration as M2 through the process of osmosis. We said that during osmosis, solvent always passes from an area of lower concentration to an area of higher concentration. But eventually when the right-hand side gets so much higher than the left, the height of this column will push down and develop a back pressure pushing on the osmotic membrane. The pressure that's required to push solvent particles back into the chamber that had lower concentration and create an equilibrium between the two chambers is called the osmotic pressure. There's no change anymore in the concentration because equilibrium means that the rate going forward is equal to the rate going backwards, or the rate reverse. Therefore, there would be no change at that point, but no change that we would see, but there still could be solvent particles moving back and forth between the left and right hand chambers due to that pressure pushing down from the height of the column. This pressure is referred to as the osmotic pressure. The symbol for osmotic pressure is the Greek letter pi. The osmotic pressure that's required to cause that equilibrium passage of the water or solvent molecules between that semi-permeable membrane is going to be a function of the concentration or the molarity, which will depend upon the number of particles in solution. Therefore, it's a colligative property. As we saw in our last image, the weight of the liquid that was in the higher column pushed back and caused a back pressure to develop, shoving some of those solvent particles of water back through the semi-permeable membrane until equilibrium was reached, and the rate of the water particles pushing forward equaled the rate of the water particles pushing backward. So there was no appreciable change at that point. Osmotic pressure then is the amount of pressure that's necessary to cause the equilibrium passage of solvent molecules through an osmotic membrane. Since it is a pressure, it will have units of atmospheres or torr or millimeters of mercury or pascals, really any units of pressure that we've seen so far. Living cells like red blood cells are surrounded by semi-permeable membranes. They'll allow the water particles to flow in and out of them. If you were to put a red blood cell in a solution that has a higher concentration than 0.9% sodium chloride, the water inside of the red blood cell will leave and go to the area of higher concentration. And this is called a hypertonic blood cell. You'll see it shrivel up and die. An isotonic solution would be where you put a red blood cell inside of a concentration that matches the inside of the red blood cell. So if you were to stick one inside of a solution of exactly 0.9% sodium chloride, it would be an equilibrium between the water leaving the red blood cell and going into the red blood cell. If you were to put a red blood cell into a hypotonic solution, this would be a solution that's lower than 0.9% sodium chloride. So imagine a pure water solution. In this case, the water would flow into the area of higher concentration, which would be flowing into the red blood cell. So the red blood cell could start getting filled with water and could burst open through osmosis. An application of osmotic pressure that's used is a process called reverse osmosis that's used to clean salt water. If we apply a pressure that's higher to the osmotic pressure and push back down on one of the chambers, we can drive the solvent into the other side, leaving the saltwater particles behind and getting fresh, clean water in one side of the chamber that are separated by a semi-permeable membrane. Let's look at the formula we'll use to calculate the osmotic pressure. Pi equals mRT. Pi is the symbol for osmotic pressure, and it will be in units of atmospheres. M is the molarity of the solution in units of moles per liter. R is the gas law constant, 0.0821 liters times atmospheres over moles times Kelvin. And T is the temperature in Kelvin. All of our units have to be correct so that they cancel with the gas law constant units. In this case, our concentration is measured in units of molarity instead of molality because we have factored the temperature into our equation. Molarity is moles per liter. Using liters, that's our volume, and volumes typically change with temperature. So if you increase the temperature of a liquid, it usually expands, whereas you decrease the temperature of a liquid, it usually contracts. So that's why we often use molality, because molality is temperature independent, whereas molarity is temperature dependent. But that's okay because we factored the temperature into our osmotic pressure equation. very dilute solution, 0.001 molar sugar in water, is separated from pure water by an osmotic membrane. What osmotic pressure in torr develops at 298 Kelvin? Using our formula for osmotic pressure, pi equals mRT. First we'll plug in our molarity, which we were given, 0.001 molar. R is 0.0821 liters times atmospheres over moles times Kelvin. And our temperature is already in units of Kelvin, so we don't have to convert anything there. 298 Kelvin. So when we plug everything in, you can double check and see that your units of Kelvin will cancel. Liters over moles will cancel with moles over liter, and you'll be left with atmospheres in this case. So pi should equal 0.0245 atmospheres. And the question asked for it in units of torr, so we can use our conversion factor between atmospheres and torr. 1 atm is equal to 760 torr. Then our units of atmospheres will cancel, and we'll end up with 18.6 torr for our osmotic pressure. Let's try another example. A solution prepared by dissolving 20 milligrams of insulin in water and diluting to a volume of 5 milliliters gives an osmotic pressure of 12.5 millimeters of mercury at 300 Kelvin. What is the molecular weight of insulin? So we're still assuming that we're doing our problems with non-volatile, non-ionic solutes, such as insulin. And initially we have 20 milligrams, which is equivalent to 0.020 grams. We know our temperature is already in Kelvin, but we have our osmotic pressure given to us in units of millimeters of mercury. We should first probably convert that into units of atmospheres. So 12.5 millimeters of mercury. And we have the same conversion that we did between torr and atmospheres as we do with millimeters of mercury in atmospheres. 1 atmosphere is equal to 760 millimeters of mercury. Our millimeters of mercury will cancel, and we end up with 1.64 times 10 to the negative 2 atmospheres. Now if we look at our equation for osmotic pressure, pi equals mRT, we're trying to figure out a molecular weight. So our molecular weight will equal moles, grams of solute per mole. We were given in the problem our grams of solute. That was our 0.020 grams. So we need to figure out our number of moles. The only term in our osmotic pressure equation that contains moles is the molarity. So we can rearrange and solve for the molarity of the solution. The molarity will equal the osmotic pressure, pi, divided by R times T. As long as our units are okay, everything will cancel and work out. So we can plug in our osmotic pressure because we already converted that. 1.64 times 10 to the negative 2 atmospheres divided by gas law constant, 0.0821 liters times atmospheres over moles times Kelvin times our temperature, which we were given was 300 Kelvin. So we can see our units of Kelvin will cancel, our units of atmosphere will cancel. We're left with liters over moles in the denominator, which it's 1 over liters over moles, so that's really moles per liter. So our molarity comes out to being 6.68 times 10 to the negative 4th moles per liter. And we don't want our molarity to plug into our denominator. We want our number of moles. So our molarity is equal to our moles of solute per liter of solution. We can call our moles of solute our X, and our problem told us that it was dissolved in 5 milliliters. So our total volume is 5 milliliters. We just have to be sure to convert that into liters. so that'll be 0.005 liters. We can rearrange and solve to get our number of moles of solute. So X will equal 6.68 times 10 to the negative fourth moles per liter times our denominator, which is 0.005 liters. Our liters will cancel, and our moles will end up coming out to 3.34 times 10 to the negative sixth moles. We can take that and plug it right back in to our molecular weight formula. So our molecular weight of insulin comes out to, we have 0.02 grams divided by 3.34 times 10 to the negative 6 moles. We get about 6,000 or 6 times 10 to the third grams per mole.